Okay, so back again looking at the 2019 Practical Geochemistry Data Analysis exam. So we're going to have a look now at question 2. So again, this is the overall mark distribution for the whole exam. So some people very well, some people not so much. But if we have a look at the breakdown for each individual question now, looking at question 2, this was one of the questions which was answered least well, I think, out of all the questions. And we'll have a look about why that might be in a sec. Yeah, so some people got the question, they understood what was going on, did very well. When I say some, I mean one person. Which was sad times for me. Very disappointed. Well, not very disappointed. Some people did okay. A lot of people did quite badly. Now, one of the reasons for this was a question about trace element incorporation into minerals and how those could be used as paleotemperature proxies. People saw this question and answered it incorrectly in two distinctly different ways. The first was they saw the word strontium and they thought, this is a question about strontium isotopes in the ocean, and then wrote an answer about the use of radiogenic strontium isotopes to tell us about weathering changes and seafloor spreading, all that kind of stuff, geochronology. And that was, I mean, the question did have the word strontium in it, but it was not asking about that at all. The other way that people decided to make up their own question and answer that was to write an answer about isotope fractionation. So this was a question about trace element fractionation, and they wrote a quite detailed, correct answer about isotope fractionation, but not one that answered the question that was asked. So they lost quite a lot of marks for doing that, which was sad times. Anyway, so looking at what we were kind of looking for. Again, a question in a couple of parts, so we'll go through those in medium detail, maybe. So the first bit of the question basically gave you a statement. So the concentration of strontium in aragonite calcite can be used as a paleothermometer, at which the measured conditions of the mineral formed. Now that's not a question, that's just a statement. Giving you some idea about the topic or area that the question is actually going to be about. So it's not about isotopes, and it's not about radiogenic kind of strontium isotopes in stable isotope fractionation or radiogenic isotope variability. It's about the concentration of an element substituting into a mineral. So looking at the first question, again, just moving this up. So using Henry's law, show that changes in the equilibrium constant, K, can be approximated by the distribution coefficient, KD. So that's what we're asking. Can we use KD, which is a thing that we can measure? It's the ratio of the concentrations of the elements in the mineral and in the fluid. Can we use that to approximate the equilibrium constants? That's the activity of the elements in the two phases, which is something that we cannot measure. So the equation over here on the left, so this is the equation for the equilibrium constant. So this is telling us something about the relative potential, relative internal energies of the system. So it's telling us about the activity of the solid, the activity of the liquid, and the ratio of those tells us about the state of equilibrium, whether the mineral whether the element will substitute or not into that mineral. Now, that's not something that we can measure. The thing we can measure is the ratio of the concentrations. So that's these X things here. These X things here. We can measure the concentrations. Now, the concentration is related to the activity by the activity coefficient. So that's this gamma. Oh no, jumped ahead. This gamma here, so the activity is equal to the concentration times the activity coefficient. Now that activity coefficient can change depending on, and sometimes can be concentration dependent. So at high concentrations, the ratio between the activity and the concentration might be different. But the important thing for trace element substitution is that when Henry's law applies, what Henry's law basically stating is that the ratio of activity constants is constant. And more specifically, that the activity constant is not dependent on the concentration, whereas for higher concentrations it may be. So in this region down here, we have a low concentration of that element. The ratio of its activity to concentration doesn't change with concentration. So any change in concentration will be reflected by a proportional change in the activity. So in that case, we can use it to tell us all about the changes in the equilibrium constant. Well, we can use things we can measure, the distribution coefficient. We can tell things about the equilibrium constant. And that's important because the equilibrium constant is something that is kind of dependent on the thermodynamics of the system. Okay. So the next kind of part of the question is asking, why are these KD values not equal to 1? And part of that reason they're not exactly 1 is this activity coefficient, so they're not, the ratio of activity coefficients isn't 1. But there's also this effect of when you are mixing these elements into the minerals, the element that you're mixing in, so this is strontium substituting into calcium carbonate. The strontium and the calcium are not exactly the same shape, not the same size. So there will be some enthalpy of mixing. Okay, so there will be some energy required to fit the strontium into the calcium, and that causes there to be a change in the activity, not the activity, the activity of that element in the little debris. Right, so that's what we were kind of broadly looking for here. So something that discussed that the substituting elements are not the same size, that substitution requires there to be some enthalpy of mixing, which causes the KDs here to be not 1, and they're not 1. They're near 1, but they're not 1. So the third, not final, third part C, then goes on to ask, why are these equilibrium constants, why are these KDs that are approximates for equilibrium constants, why are they dependent on temperature? So why is it that we can use the ratio of an element in a mineral as a proxy for the temperature at which that mineral formed? So the first thing is that we can approximate KD with K. So we've already kind of addressed this in the previous part of the question, but worth stating again that that KD is an approximation of the equilibrium constant, and we can link the equilibrium constant to the kind of the thermodynamics of the system with this kind of equation down at the bottom, which we've seen a number of times in this course, geomaterials and other geochemistry type courses, where the free energy of a system is equal to this minus RT log of the equilibrium constant. Good. And that free energy is composed of these different parts. So there's an enthalpy term, there's an entropy term, there's a volume change term. So the volume change term we can kind of ignore because we're only substituting very small amounts of a trace element into a mineral, so that's not really changing the physical properties of that mineral, having to expand or contract too much to fit these small kind of trace quantities of element into it. So we can put that one in the bin, as it were. We can, or the ideas fridge, and snack on it later. We can ignore this change in volume term or not. Doesn't really matter. But if we just look at this equation here, we've got a range of thermodynamic properties. We've got equal to something with the equilibrium constant in. So we can kind of rearrange that, divide both sides by minus RT. If we want to. We could do some separating out of terms or not, doesn't really matter. But the point is that if we've got log k equals this thing over here, which is a fraction with RT on the bottom, we can raise e to the power of both sides to get rid of that natural log. And that gives us an equation that looks something like this. But the important thing here is that if we look at the form of this equation, as the temperature is increased, okay, that makes this whole fraction here start to tend towards 0. Okay, and e to the power of 0 is 1. So at higher and higher temperatures, at least this part of this equation here will tend towards 1. There is some kind of entropy term here, which means it doesn't exactly go to 1, but nonetheless, we can see from the examples that we had in the lectures that the KD for aragonite, strontium incorporation into aragonite, is about just a bit above 1. So actually, strontium preferentially goes into the aragonite structure. But at higher and higher temperatures, this tends towards 1. So we tend to get less strontium incorporation as we go to higher temperatures. Whereas for calcite, it's the other way around, in that strontium is slightly incompatible into the calcite structure. But at higher and higher temperatures, we tend to 1 with this KD here. So the amount of strontium that you can get in goes up with temperature. So having some explanation of that, maybe bringing in some of these examples would have given you the big box. Okay. And then the last part of this question brings in some of the stuff that we did with diffusion. So why the strontium concentration is preserved in growth layers, in shells, corals. Why does that last? Why doesn't that kind of go away somehow? So what we were really looking for here is a statement that the element ratio that's incorporated into the calcite or aragonite is fixed at the time of formation, and that strontium, once it's inside the shell, it can't diffuse out again because the rate of diffusion is very, very slow at regular temperatures, and to get it to diffuse fast enough to be, to change its element ratio on any sensible geological timescale, you have to get the sample very, very hot, okay, which would effectively destroy the coral anyway. So you could have also talked about other types of diagenetic alteration, kind of recrystallization of aragonite into calcite during kind of meteoric exposure of corals. If you really wanted to, that would have been an extra detail that you could have gone into. But what we're really looking for here is kind of reflection of the practical that we did on this, which was that the diffusion of strontium through aragonite or through calcite is a very slow process compared to geological time at normal kind of Earth temperatures. Okay, you have to bury it quite deep in the ground to get hot enough for diffusion to really start messing with your thing. So we get our strontium from seawater that gets deposited in the very surface layer of the coral, depending on the strontium concentration in the seawater and the temperature, determining what that K value is. And then when the next layer of coral grows at maybe a different temperature, different seawater chemistry, that layer is fixed in its composition. There's no diffusion of strontium in between these layers. Even on a micron scale, it's just too slow. Okay, so those were the things we're looking for in question 2. And I think most people did very badly on this because they didn't answer the question. They answered another question which they had revised, but not answered the one that was written down. So don't do that. It's bad. Okay, stop. Stay tuned for the answers to other questions in other videos. they'll be just as exciting, maybe more exciting. Who knows? And